All right, so I'm here today to talk to you about the magic of databases. And one of the reasons I wanted to talk about this topic is at my current company, Central, which I'll talk a little bit about later. We work quite a bit with bootcamp graduates. And one of the things that's always sort of missing from most people's development experience, but especially bootcamp grads, is what's going on at the database level. And that's really because like you're cramming a lot of knowledge in a very short amount of time. And the thing that I've learned in the technology field is that you're never going to know everything. There's just so much stuff out there. There's just so much different technology. Hey, we got our first video. How you doing? Um, so it's super hard to get a grasp on everything. Now we've only got like 45 minutes together, so I'm going to be blowing through topics fast, right? So don't feel bad if you don't grasp everything. I'm going to cover a lot of stuff at a high level. What I really am trying to do is to introduce you into terms and concepts, so that when you run into a problem, not that you instantly know how to solve it, but that you go, I remember this weird dude was given a video presentation and talked about table statistics. Let me Google that because I remember that, and see if some of the things and the ideas that I have mentioned sort of pop up in your memory. All right, sounds good. Here we go. We're off in the races. Um, so a big thing that you hear, not so much anymore because people feel like the NoSQL camp is one, but relational databases versus NoSQL databases. You hear a lot about Postgres, MongoDB, MySQL, Cassandra, SQL Server versus React. I think the real crux between these two technologies is really like consistency versus what I call flexibility and scalability. When you look at these old relational database systems, um, they can be a little more cumbersome to scale when you get into large uh, footprints, predominantly because of the guarantees that a relational database and a transactional database gives you versus NoSQL, where there's a lot of flexibility with things like MongoDB. And MongoDB has actually come a long way specifically in being able to offer some of these transactional guarantees, but they don't really solve the problem or add anything new to it. They simply introduce the same constraints, and we'll talk a little bit about that later. So, depending on your work, you might be a NoSQL fan, you might be a relational database fan. I tell you, relational databases are here to stay. The one thing that I want to make sure that I mention as I go through this is that there is no right choice. It all depends on your application. So one is not better than another. The same way a hammer is not better than a screwdriver. It all depends on the problem that you're trying to solve, and the particular domain that you're dealing with. The example that I always give is if you've got a document store sort of database, right, and you're building a financial application like a bank ledger, a relational database makes a lot more sense because you have a single row that has the current balance, and you can ensure that you update a debitor and a creditor's accounts in a single transaction at once, right? Whereas a document store, because of the nature of it, you might structure it a little bit differently, and you end up shifting a lot of the complexity of managing that transaction into your application versus into the database system. Remember, complexity is never really destroyed, it's just sort of moved around. So when you're using NoSQL databases, sometimes you have to take on the complexity into your application. With a relational database, sometimes you're offloading that to the relational database system, but now your application is left to fend for itself for other purposes. So, um, so the name of this talk is the basic functions and pitfalls of relational databases like MySQL and Postgres. In this talk, I'm going to talk specifically about Postgres because I have the most experience there. But I assure you that every component that I talk about has a MySQL component to it, just by a different name. But the functionality is almost identical in terms of the purpose that it serves. So the first thing, disk is slow. And most of the optimizations in relational databases, really any database, but specifically SQL databases, most of those optimizations are geared towards, oh, I'm going to mute you, Spence, because we got a little feedback coming from you. But if you have a question or anything, feel free to unmute. Um, most of optimizations and a lot of stuff we're going to talk about is really to deal with the fact that disk is slow, and we want to avoid going to disk as much as possible with a relational database. But you say, Jeff, how slow is slow? Well, here's the deal. When we're talking about nanoseconds, it's really difficult to sort of really comprehend the difference in speeds because it's so fast to us. So what a genius man by the name of Brendan Gregg did was he took latency numbers and he scaled them to 1 second. So we took a CPU cycle, which is the fastest, or at least when he wrote this, was the fastest operation that there was. We scaled that up to 1 second and then scaled everything else up accordingly to sort of give us as humans a better understanding or concept of how much time we're talking. So if a CPU cycle is a single second, accessing main memory is 6 minutes in terms of time, right? So that just gives you an idea of just how much of a difference in performance we're talking about. If we're talking about going to solid state disk, solid state, the fast disk drive, you're talking anywhere between 2 and 6 days, depending on the latency of that device, right? If you're talking about a rotational disk, that jumps up to 1 to 12 months, right? If you have to do a round trip on the internet from San Francisco to New York, 4 years, and you can just see the numbers get, bigger and bigger and bigger, all the way up to a physical system reboot, which takes about 5 minutes. In computer time, in our scaled up ideas, that's 32 millennia in CPU clock time. So you just get a better understanding and a better idea of just how slow disk is compared to memory and compared to CPU cycles. And that will help set the context of why it is so important that we avoid disk access as much as possible. So when it comes to relational databases, we talk about ACID compliancy. And ACID stands for atomic, consistent, isolated, and durable. Those 4 characteristics are what define relational databases. And we'll go through each of those individually. So when it comes to atomic, we're saying transactions are treated as a single unit. They either succeed or fail together. Going back to the banking example, if you were going to transfer money between 2 accounts in your banking app, you would never want a scenario where the update to the sender's account succeeded, but the update to the receiver's account failed, because then you've got this imbalance in dollars, right? In reality, you need those transactions to happen at the same time, and you need them to either fail or succeed together. So that's what we mean by atomic. And as you get with bigger applications, you might find yourself updating anywhere between 20 and 30 tables in one go as part of a transaction. And you need to make sure that that all happens together at the same time. Consistency is basically transactions can only move the DB from one valid state to another. That's just ensuring that you don't have half a write or something like that, right? Where it's like, oh, this row was supposed to have 4 fields updated, but only 2 of those fields actually updated because part of the write failed. Consistency is about ensuring that, the state is valid as we move through it. Isolation is the ability to serve concurrent executions. And what we mean by that is specifically like transaction isolation. So going back to the banking example, say we've got multiple transactions going, right? And we've got Bob, who is who wrote a check, but is also at the ATM machine, right? If both of those transactions could affect each other, right, then the state of Bob's account could be different in between those 2 job runs, right? We need to make sure that these things can happen in isolation, and then we sort of reconcile afterwards. So if I was doing a debit and a credit on the same account, right, I would want to make sure that when I updated that record, there was some sort of locking mechanism that prevented me from both debiting and crediting the account at the exact same time, because then I might end up with an incorrect dollar balance. Durability, and this is one we're probably going to focus the most on, is once a write is committed, it will remain committed. Meaning, like, once I write this data, I feel confident that this data is in the database and it's not going to be lost as part of some system failure. So with all of that, that was just to sort of set up the talk. I'll introduce myself really quickly. My name is Jeff Smith. based out of Chicago, Illinois. I'm currently the director of production operations for a company called Centro here in Chicago. We're a digital advertising software firm. So we basically, this sounds terrible, but we basically help follow you around the internet to sell you more things, right? So if you ever saw like, the ad for a pair of shoes that you bought 6 months ago, we might have been involved with that some way, shape, or form. But the advertising space from a technical perspective is incredibly interesting and incredibly vast in the amount of challenges that we have, especially with privacy becoming more at the forefront than us trying to respect people's privacy while at the same time being able to compete in the marketplace. So it's a really interesting time. If anyone's looking for work, I would highly recommend you check out Centro at centro.net, or shoot me a note. I'll leave my contact info at the end of this talk, and Matt will also upload that to the meetup site. Previously to that, to Centro, I was at Grubhub, where I helped build out the site reliability engineering team there. I just finished a book that got published back in November, Operations Anti-Patterns, DevOps Solutions, and you can catch me at my never promptly updated website, attainabledevops.com. So I've been doing this for about 20 years now, and it's still fun. So the first thing we got to talk about is the buffer pool. So in databases, there's this concept of a buffer pool, and the buffer pool is basically a dedicated section of memory that stores table data. And the whole idea behind the buffer pool is to have this data that is frequently accessed, to have it cached in memory in such a way that so when someone requests it, we don't have to go to disk, because as we laid out in a previous slide, going to disk is extremely slow. So the way the buffer pool gets populated is when someone requests data from a table. So you do a select star from auth user, let's say, right? The first thing the database engine does is it says, is this data in the buffer pool already? If it is, it reads it from the buffer pool and gives the data to the client. If it's not, then it needs to figure out where that data is on disk, read it from disk, then add that read data to the buffer pool so that the next time you read it, it's there, and then we serve that data to the client. It's a very simple caching mechanism on the surface, right? We're basically reading something from permanent storage into memory so that subsequent reads are faster. So you'll notice that if you ever reboot a database server and then you start querying it, the first set of initial queries are slower because the cache or the buffer pool hasn't been warmed yet. So it doesn't have a lot of the data that is frequently accessed. And if you look at a database system over time, you'll see that applications sort of settle into a pattern and they end up fetching the same amount of data over and over again. In our database system, our cache hit ratio is fairly low because of the nature of our database, and we still serve 90% of requests from the buffer pool without having to go to disk. So that just gives you an idea of just how predictable applications can be. So when we talk about storage, there's actually multiple layers of storage, right? You've got the physical hard drive, right? So that's where the bits, the zeros and ones, are physically located on either a spinning disk or a solid state drive. When those files are read from the operating system, the actual, most likely Linux, but or Windows operating system, that data gets loaded into a file system cache. So basically exactly what the database server is doing with tables, the operating system is doing with files. So if you're Linux users, if you ever looked at free memory, you might see a spot that says buffer/caches. That's telling you that this is memory RAM that I'm using for the file system cache. So if you need it, I can give it to you because I'll just empty out that cache. But by having the operating system use memory to support like commonly read files, it saves a trip back to the disk every time someone requests the file. And that's at the operating system level. Then you've got the Postgres database where they have shared buffer caches. And the shared buffer caches are Postgres's scratch pad of storing data. So when you think about it, whenever we have to read data, right, we're going through these multiple layers. We're checking the shared buffer cache. When that doesn't work, we're reading from the file system, but in reality, we're reading from the file system cache. And the operating system is saying, yes, I've got that in cache, here you go. Or if it doesn't, it's saying, all right, now I'm going to go to the spinning disk and feed you that. So as you can see already, there are multiple layers of the environment that are geared towards preventing you from going to disk because it's so slow. Writing to the DB is very similar. What's surprising to most people is when you update a record in a database, the first place it actually gets updated is in memory. It doesn't actually get committed to disk right away. So what will happen is when you request the data, we'll fetch it from the data pool, buffer pool. If it's not there, we'll read it from disk. If it is there, we add it to the buffer pool. But then what we also do is we update. So let's say you're running an update statement like update employee, set department equal to the technology. This entry, this update is written to the object in memory in the buffer pool. Only later does it actually get serialized to disk and then ultimately flushed into the hard drive. So when we update a record in the buffer pool, the database engine marks that record as dirty, basically saying like, hey, this page, this slice of memory has been changed compared to the version that's on disk, and we're going to have to write it to disk at some point. At some point is the key here. But then it's like, but if the server crashes, if that update is only in memory, what happens? We lose the data, right? Well, databases have a way to deal with that as well. Again, going under the mantra, disk is slow. So we're always trying to optimize for disk performance. When it comes to writing to disk, there's basically two types of access patterns. There's sequential access and there's random access. Sequential access is literally, I go to the end of the file and I append to the end of the file. That's incredibly faster than random access, where you might have to read between a few blocks. So using this diagram as an example, you can see where, let's say we want to read, we need to read 2 blocks, right? We need to read file 4 and file 7. Now, maybe this file was split up across 2 blocks because there wasn't enough contiguous space to store this thing. Well, first the disk head needs to move to position where file 4 lives. It's got to read that data, then it's got to write it, then it's got to move to position file 7. It's got to read that data. It's got to write that data. In a sequential file, we could just go all the way to the end of that file log and write our new record. And this is exactly what happens when you write an entry into the database to make sure that it's not lost when you reboot. And this concept called the write-ahead log. That's what it's called in Postgres. In MySQL, it's called the transaction log. In SQL Server, I think it's called the T log. Every database, relational database, has this concept. But basically what the write-ahead log is it's a special file that's write records of all the changes that have been made, and they are immediately flushed to disks, okay? So when you dirty that record in memory, when you update that row, what happens is the database system says, okay, I need to write the fact that we changed this record to the wall, to the write-ahead log. So the write-ahead log will have an entry in it that says, hey, Jeff just updated record 5 in the employee table, and he set this value. This is done to ensure that if the database crashes, we still have a record of those changes that have happened, even though we haven't moved it to disk. Now you may ask, well, why don't we just go ahead and write it to storage right away? Well, the problem is because we have a durability guarantee with the client, that's the D in ACID, we cannot tell the client that the write was successful until we've actually committed it to disk somewhere. If we were to commit it to the actual table storage where it will finally live, it will be a slow operation. Why? Because the table is accessed randomly, right? So what we would have to do is we would have to seek through the file to find exactly where that record lives and update it there. That is incredibly slow, especially when you have a client waiting for confirmation. So what we do instead is we write it to this log file and tell them, yes, your write is successful. Now they don't know that it hasn't actually been persisted to final storage, But because of the way the relational database system works, it is viewed as if it had been committed. Sure, there's a couple of extra reads that happen behind the scenes, but still, when you look at that table, it will look as if it had been updated. But more importantly, in the event of a crash, we can always replay that write ahead log to know that we can always replay the write ahead log to basically get the database up to the point that it should be before the crash. So basically, this is outlining what the write ahead log process is, right? An update is applied, we update the shared buffer, we record the buffer flag, we flag the buffer as dirty for that particular page, and then we write the update in the write ahead log. Boom. Once we do that, we can tell the client that we're done and the client can move on about its business. But then the question is, how does the data get written to the actual DB data files? Well, in all database systems, there's this concept of a background writer. And the background writer is responsible for reading the write-ahead log, seeing what records need to be updated on permanent storage, and doing that process. But because it's in the background, we can tune that process so that we don't overwhelm the database server. Because you don't want a scenario where you're constantly writing to disk, and as a result of all of those writes, you're slowing down traffic for users. So the background writer has a very sophisticated algorithm. It uses what's called a least recently used algorithm, and it looks at memory usage statistics to determine how many pages from the write-ahead log it can take and flush to disk. The write-ahead log has a series of checkpoints as well, and the checkpoints are basically a pointer for the background writer to know what in the write-ahead log has already been written to disk and doesn't need to be reprocessed. But the catch is, even after the write-ahead log and the background writer does that, your data still technically isn't on disk. Why? Because you've written it to the file system cache, right? The background writer is interacting with the operating system sort of, through APIs essentially, right? And the APIs are basically doing exactly what we're doing at the database layer with the client. It's accepting the write and saying, okay, I got you. Don't worry about it. Continue on. But it hasn't actually made its way to disk yet. So there's two different ways that we can solve for that in the database engine. We either configure the database engine to say, every time I write to disk, you have to flush that write to disk immediately. Basically saying, ignore the system cache, write to disk immediately. That has a increased level of durability, right? Because now you know that that is being committed to disk, but it also slows the system down because now you're doing writes all the time. The other option is you can leave it up to the operating system, who has its own caching algorithm, which will figure out when the most opportune time to take what's in the file system cache and flush it to disk. That's the most performant method, but the catch is there is a window where if you were to crash, it's possible that data that was in the file system cache hadn't been persisted to disk yet. Does that mean we lost the data? No, because we have it in the write-ahead log. And the write-ahead log is ensuring that it's been flushed to disk. But it hasn't been moved to its permanent storage location in the actual table storage. All right, so now we'll move to actually executing queries. When you run queries, there's a lot of things that go into that. And what's interesting is, even though we're telling our database system like what we want from it, SQL, the language that we use to communicate with the DB server, is what we call a declarative language. And what declarative means is we're not actually giving it the exact instructions it needs to do or execute to give us the results that we want. We're defining the result that we want, and we're leaving it up to the database engine to figure out the best way to do that. The way that database engines do that is with a part of the database engine called the query planner. And the query planner is basically responsible for taking the SQL that you've given it and figuring out the best way to retrieve that data. The query planner outputs what's called an execution plan. And this is all transparent to you as both a user or an engineer. There's ways to peek into it, but for the most part, it's pretty transparent. But the query planner will put together an execution plan, and the execution plan will detail exactly what needs to happen. So I said viewing a query plan, but this is actually viewing an execution plan. So there's two commands that allow you to take a look at what the query plan that gets generated. There's explain, and then there's explain analyze. And the syntax is basically explain or explain analyze in the query that you want to run. The difference between the two is explain will look at the query, look at statistical information that it knows about, and then give you the plan that it generates. The catch, though, is when you're actually running a query, depending on the complexity of the query planner might at runtime have to make a decision that it can't make until runtime. So the actual query plan that gets executed is different than the query plan that it would present you if you just didn't explain. So what explain analyze does is it actually executes the query and then tells you this was the plan that I used to execute it. And sometimes those are different. So if we look at this explain, this query plan, you can see a bunch of what the query plan is made up of. You can see that I'm using like a film database here. Let me switch. Can you see my terminal? Yeah. So like I'm looking at a sample database here. So if I do a select star from film, format it so it actually looks readable. So here you can see all of these records for films, right? So if I did an explain on select star from film, if I spelled explain correctly, that would go a long way to making this work. We can see the query plan. And here it's telling me it's going to do a sequential scan on the table film. And here we see a little bit of cost information, right? And what that cost information is, it's basically a relative calculation of how expensive this particular query is, okay? Now, sometimes if you've got a query plan, that if you've got a query that's extremely long, there might be multiple steps to it. And you'll see multiple entries like this, detailing everything that it does. So in this example, you'll see the cost is 0.0 to 64. That basically means this particular segment costs 64 of these imaginary relative points. But this becomes useful to you as a debugger, because as the queries get more complicated and you have more substeps, you can see which portion of the query is spending the most amount of time or is the most expensive, and you can try to optimize that. Unfortunately, I didn't have time to put together a more complicated example to show you a more detailed query plan, but you know, we can visualize it. Rows is basically how many rows had to be read to get that data, and width is basically, you know, like how many columns. It's usually less. Rows is usually the one that we care the most about, because we're curious, like, you know, how many rows are we actually going through? Because the more rows we go through, the slower things get. Okay, so how does the query planner decide what to execute? As we said, so the same query can produce different execution plans leading to different levels of performance. So you might have a query that has been running fine for years, and then one day a database admin says, yeah, this query sucks. And you're like, I don't understand, this query's been running the same, haven't touched it in years. What happened? Query plans are influenced by a couple of things. One, they're influenced by the number of rows in a table. That's known as statistics. And we'll talk a little bit about that later. But query plans can also change based on joins and different indexes that you use, right? So just a quick refresher in case you haven't worked with them. What is an index? An index is basically a lookup table that makes it easier to find data in a table. So you can index a particular column in your database to identify like, hey, this is a field that I constantly query by. So like, let's take a look, if I go back to terminal, let's take a look at the film table. Okay, so the film table has a column of film ID, title, description, release year. Okay, if I'm constantly querying by film ID, I might want an index on that. Why? Because the index will allow me to query that table much faster. And you can see that in certain query plans. And I'll show you an example in just a minute. The catch with an index is the way an index is structured, though, it is basically a pointer to where that record lives on disk or in memory. So I don't know, you guys might be too young for phone books, but like, you know, when you look at a phone book for a number, right, if you go to the index page, it really cuts down drastically as opposed to having to scan through the entire phone book or even the dictionary, right? The problem is, though, you end up reading twice, right? You read once to read the index, then you've got to go to where the data actually lives and read there as well. In most scenarios, that's still incredibly faster than scanning through the entire table. So if an index is defined, your query planner will try to use it automatically, but you have to write the query in such a way that it's actually helpful, that you can oops, sorry, forgot to go back. When you're using an index, if you've got the index defined, the query planner will attempt to use it automatically, but you have to write your query in a helpful manner, in a way that the engine will understand how to use it. Let's do this. Actually, we'll go back to terminal. Let's do, can I move this without messing you guys up? Yeah. Select star from film where description equals, oh boy, let's not do that. Select star from film. Okay, we'll take this guy. All right. So if I say select star from film where description equals, right, I get a single record. That comes back pretty quick. If I do an explain on that query, I see that I did a sequential scan on film. And a sequential scan basically means I read every single row in the table to find the record that I was looking for. Oh, sorry, we got a few people joining. So I did a sequential scan to find that record. Now, let's say I wanted to do it by ID. If I do select star from film where film ID equals, what was that film's ID? What equals 133. And if I actually do the explain instead of just doing the query, you can see here I'd used an index scan, right? It automatically leveraged the index and it found my index condition of 133 and it returned it back. But more importantly, we can also see the relative performance benefits, right? Because here we had a cost of 66.5 to deliver the same record. But here, the cost was 8.29. As your queries get more complicated, those savings really begin to add up. So different ways that you specify the query will allow your query engine to use an index. So think about that. If you're ever doing some SQL and you're like, why isn't this using the index that I defined? Look at whatever database management system you're using, whether it be Postgres, MySQL, SQL Server, and just look for how the query planner for that particular database engine looks at joins, looks at index usage, because sometimes you can structure a query in a way where the query planner isn't smart enough to figure out that there's an index that it could use. So that's a great idea of where like the explain, analyze can come into effect, because it's like, oh, you're not using an index. That's why this thing is so slow. We just talked about that. So the elephant in the room too is like try to avoid table scans if you can. Sometimes you can't, but a table scan is always the process of reading the table from the very beginning to the very end, right? Looking for the records that you care about. And the reason that becomes problematic is a couple fold. One, uh, it's slow, right? But the other thing is every record read gets loaded into memory, which means possibly another record has to leave. So if we've only got 5 gigs of RAM, right? And we say, oh, I'm going to do a table scan on this table, on this 10 gig table. Every record we read is going to come in. But if we're at memory capacity, that means the database engine has to figure out what record to evict. It has to get a record out. But what ends up happening though is if you're what we call thrashing the buffer pool, right? If you're doing that constantly, other queries that are running on your system aren't getting the benefit of their most recently or regularly used records being in cache because your query has forced them out because it's doing a table scan on a large table. So aside from them being just generally slow, you can also end up impacting the system if you're not careful about when your queries are doing table scans and how problematic they might be for other users in the system. Sometimes you can't avoid a table scan. Sometimes it's actually faster to do a table scan. We'll talk about that in a little bit. Um, so we were talking about like when you join tables. So a join is basically in a regular normalized database, you might have data that exists spread across 3 tables, right? So if we're looking at this salesperson um, uh, diagram, we can see that we have the salesperson defined in one table, the sales defined in another, and the product defined in another. So if we wanted to identify all the sales done by people over the age of 30, right? We've got to join the sales table and the salesperson table into a single table in memory so that we can scan that. Doing that by index, doing that with indexes is incredibly helpful because it allows you to eliminate records quickly, but how you join those tables and how you specify that join will impact the query planner's ability to actually be able to leverage those indexes. And remember, like I said, I'm throwing a lot at you. I'm not saying that you're going to remember all of this when you get out of it, but hopefully hearing it, you'll remember like, oh yeah, there's something about when I join, if I want to use an index, there has to be a particular order. Table statistics is another thing that we sort of talked about. So table statistics is a mechanism to track the size of tables, right? It tracks a bunch of other metadata, but the size of the table is really an important thing because it can influence the way the query planner actually operates. And a perfect example is, let's say we've got a row, a table called film table, and we've got an index on that table, right? If there's 5 rows in that table, that means we've got 5 index entries as well because we have an index entry for each table. If I say, give me all the records from film table, it doesn't make sense for me to use the index. Why? Because I need to read every row anyways. If I use the index, I've got to read the index, then I've got to read the record, and that's 2 reads when I could just read the data directly, knowing I'm going to read the entire table. Sometimes though, it's also beneficial just to scan the table for performance purposes. So let's say I said, give me all rows that were released after 2012. With only 5 rows, there's a good chance that it's going to be faster for me just to read the table directly than to read the index, check the value, right? Because essentially I'm going to have to, again, do a double read. So what could have been 5 reads where I read the entire film table and threw a bunch out could end up being, 10 reads if I do it via the index and everything matches. So sometimes the query planner will opt for a table scan because it's more efficient, but that's only based on the table statistics. It doesn't actually query the table at runtime to know how big the table is. And the reason that's important is because sometimes table statistics get out of whack. Over time, every database will run table statistics periodically to update them. But what will happen is over time, these statistics can get out of whack. So if you do lots of inserts into a new table, right? If you're inserting a bunch of new records, suddenly this table becomes larger, but the statistics and the query planner thinks it's only 20 records. So it may say, it's easier for me to just read all 20 records. But lo and behold, when it actually executes, it's reading, 5,000 records. Lots of deletes. Same way, opposite thing, right? Where it's like, I'm not going to table scan this thing because it's so big. But then it turns out you deleted a bunch of records and the table is actually much smaller, and the query plans end up doing more work than it actually needed to. Every database engine has a way to run statistics manually. You can run statistics on a specific table, or you can run statistics on the entire database. A time when you think that you may want to run statistics manually is when you've done a lot of inserts of new records, a lot of deletes of new records, and you plan on querying that table very soon after that. Or if the query planner seems to be using some odd query plan that you just don't quite follow. If you go like, why is it doing a table scan here when it could be using this index or whatever? Make sure that the table statistics are up to date. Another interesting fun fact is if you back up a database and then restore it, usually the table statistics are out of whack because there's a bunch of data in the database, but the table statistics is not always part of the database backup depending on your database engine. So depending on how you do your backup, your table stats could be way out of whack when you restore the DB. And you may be like, wow, every time we restore this database, the first hour to an hour and a half, it's slow, but then it picks up. Well, it could be because your table statistics are out of whack, so your query plans are bad. And then after a while, the statistics get updated as part of the automated process. So like I said, I know I went through a lot. So I'll give you a quick, brief recap. I will share these slides with Matt. Databases are designed to avoid disk IO, minimize it as much as possible. Understand your query patterns, define indexes for them, especially for fields that you're heavily querying over and over again. Make sure that those have indexes to lessen the strain on your database engine. And then use explain and explain analyze to understand poor performing queries, to get an idea of where they're spending time and places that you might be able to optimize and make them better. So that's all I got. I know we're getting close to the hour, so I just wanted to say thanks, everyone. Sorry for those that showed up late. The presentation is being recorded, and I believe Matt plans on making it available. If anyone wants to reach out to me, best ways are usually via email, jeff@attainabledevops.com, or on Twitter at Dark and Nerdy. I think we have a few minutes for questions. If anyone has anything they'd like to chat, discuss, clarify, anything like that, I'll open it up. Just feel free to unmute yourself, maybe go on video. No pressure though. You are quite welcome, Sally. All right, well, Spencer, you crossing the line?
Yeah, can you hear me?
Yep, I can hear you.
Yeah, I asked a question earlier about how do you assign the index? Is it just a new column with integer numbers for each row?
Yeah, so with an index, what happens is there is a command, and it's usually create index on, and then your table name, and then your column name, and it will go through and create that index. I don't want to do it on this guy because it does take up some CPU, but let me, if I can.
I think your screen is cut off, like at the bottom.
Oh, you don't see it? Oh, okay.
Yeah. Yeah, it's still cut off.
Really weird.
Okay, now I see it.
Okay. Yeah, so it's usually like create index on, I think with Postgres, it's like then table name and then the column name. But it'll vary based on your database system. But that will go through and scan the table and then end up creating an index for it. And then the index will be named. And you can see here where we've already got a few indexes created. um, you'll see the indexes listed where it's like, the index name is film underscore p key. It's a B tree index, which is a bit more involved, and then the column that it's indexed on.
So if you already have a database with a primary key, you don't need to do this, or should you
Correct.
still do
Yes.
it?
If your database has a primary key, then chances are the index already exists. There are a few systems that don't create the index with the primary key, but that's pretty rare. You can always check by describing the table. I don't know what database systems you use, if it's Postgres or MySQL or SQL Server,
It's
but
Oracle.
Oracle. Okay, that's the one I have the least experience with. So good luck. but uh, but yeah, there should be a way to define to describe the table, and from there you'll be able to see what indexes exist. But I'm almost certain with Oracle, if you define a primary key, it automatically is indexed.
Okay, nice. And then I had another question actually. Can you provide a simple yet concrete example of, when you would, without a doubt, use NoSQL over SQL or vice versa?
Yeah, I would use, all right. So one, scale would always come into play, right? So like, the problem with like relational database with SQL is that scaling for writes is always problematic, because you usually, there are some multi-master setups, but they're a little janky. So you're usually constrained by the write speed of one particular server. So that has a bunch of different availability constraints. For me, I would reach to NoSQL when I could really denormalize the data that I was dealing with, and store it as like a single document without having to, for performance purposes, join across multiple tables. So a lot of it would also depend on my reporting. So I'm trying to think of a very specific example. So a very specific example is like, we have a database where we store environment information in it. And the environment is basically like what the environment name is, when it was created, who created it, what components exist on it, right? I would never want to report across environments in any way, shape, or form. That data is like an atomic unit together. So putting that in a document store like a NoSQL store would make a lot of sense for me, because I can retrieve, update that document, only save portions of it. But then more importantly, as I need to distribute my application, as I go into different regions in AWS or whatever, I can continue to grow the database across those regions without having to worry about scaling the master for writes. Um, so that's like one specific example in my experience.
Okay. So if you don't mind, so I work for some scientists and biologists in a lab, and they conduct some experiments, and they basically store a bunch of the experiments parameters in a database. And so would that also be an example where, because there's never a case where you would use, one experiment's parameters into another one. So would that fall into that case too, where
Yeah,
it's better in using NoSQL?
I could totally see that falling into that case. I won't go as far as to say it's better, but it's definitely an option. The one thing that I always caution people with NoSQL is, um, you pretty much have to know how you want to view your data when you build your schema. And if you have uncertainty, in my opinion, you're better off going with a relational database. So if you know the reports that you're going to generate, if you know the way the application is going to access, retrieve, and update this data, then NoSQL becomes an option. But if you've got a little bit of uncertainty, I always opt for a relational database, just because that reporting flexibility is much easier to deal with. Um, it's easier to deal with the unknown and new use cases in a relational database for me than it is with NoSQL, because with NoSQL, then I might need an entirely new representation of the data, which means I've got to persist it differently, right? I might store the object. A common pattern is like, you store the same object in different fashions based on your reporting needs, and it's usually easier to do that if you know all those reporting needs up front than um,
Hmm.
versus having to do it on the fly.
Okay, thanks.
Yep. Oh, I see the chat lit up, but I missed it. Um, cool. Anybody else have any questions? All right, sweet. Well, thanks for having me. Again, I'll be sharing the slides with Matt, and he'll be posting it to your group. I think I'm coming back on the 18th of June to talk about TLS security and web security. If that interests you at all, then maybe we'll see you then. If not, take care and have a good one. Stay
Thanks,
safe.
Jeff.